Welcome everyone to today's Explainer. Today we are taking a topic that frankly frustrates a lot of developers, and we're making it entirely practical: public key infrastructure and X.509 digital certificates. Listen, if you've ever just stared at a completely confusing certificate error in your terminal, or maybe you've wondered how your browser actually knows it's talking to the real GitHub and not some highly sophisticated imposter, well, you are in the exact right place. We're going to unpack the cryptography and the underlying architecture that secures modern internet communication.
Okay, let's dive into this. Here is our agenda for today. Number 1, the public key problem. Number 2, inside the X509 certificate. Number 3, common certificate formats. 4, the chain of trust. And finally 5, verification and revocation.
Section 1, the public key problem.
Right, so before we can truly appreciate the solution, we have to deeply understand the threat. When we're building distributed systems, microservices, or web apps, we are constantly establishing secure connections over the internet. And let's be honest, the internet is a network that is fundamentally insecure. We rely on asymmetric cryptography, right? Where every server has a private key that's kept completely secret and a public key that's meant to be shared freely. But this creates a massive vulnerability. Over the internet, how do you actually know who really owns a public key? If you request a public key from a server over an unencrypted channel, how do you prevent an attacker from just intercepting that request and handing you their own public key instead? The stakes are absolutely massive here, because if you encrypt your sensitive data with the wrong public key, you aren't securing it at all. You are literally wrapping it up in a nice little bow and handing it directly to the attacker, who holds the matching private key to decrypt it.
And this brilliantly illustrates exactly what we are up against. This is a classic man-in-the-middle attack. So, step 1. The client application asks for the server's public key to establish a secure connection. Step 2. An attacker, acting as a network proxy or maybe lurking on a compromised Wi-Fi network, intercepts that request and quietly forwards it to the server. The server, completely unaware, sends back its legitimate public key. But at step 4, that is where the critical moment occurs. The attacker intercepts the server's legitimate public key, throws it out, and sends the client their own public key. And the client is completely fooled. The client then uses the attacker's key to encrypt the session, and from that moment on, the attacker can observe, decrypt, read, and even modify everything exchanged over what the client genuinely believes is a secure connection. This is exactly why we can never, ever blindly trust a raw public key.
Section 2, inside the X509 certificate.
So, to prevent that devastating man-in-the-middle attack, we clearly need a reliable way to definitively bind a real-world identity to a mathematical public key. We need a digital ID card. And that is exactly what an X.509 digital certificate is. It's essentially a tamper-proof data structure that securely attaches identity metadata to a public key. The X.509 standard dictates very specific, universally recognized field names and semantics. By deeply inspecting these standardized fields, any client application, whether that's a web browser, your mobile app, or a backend microservice, can definitively determine exactly who a public key belongs to. This makes it practically impossible for an attacker to successfully swap keys without triggering massive, unavoidable security warnings.
Now, what's really interesting about this slide is how the X509 standard maps perfectly to something we all use in the physical world to prove our identity: a passport. The subject field identifies the owner of the public key, so think of this as the citizen holding the passport. The issuer field identifies the certificate authority, or CA, that created and signed the certificate. This perfectly represents the issuing country that vouches for the citizen. And finally, the validity field sets the strict time range the certificate is valid for, which is exactly like the expiration date stamped in a physical passport. When you map it to this real-world concept, the abstract cryptography of PKI suddenly becomes incredibly intuitive.
Let's examine that identity binding just a bit closer. Historically, the X509 standard was originally designed way back in the 1980s for X500 electronic phone directories. Because of that legacy, the base subject field looks kind of like an archaic mailing address, with components for country, organization, and organizational unit. But today, for securing modern internet connections, web browsers and operating systems rely almost entirely on an extension called the SAN, or Subject Alternative Name. The SAN extends that rigid subject field by allowing an array of modern identifiers. We're talking primarily DNS names, but also email addresses and URIs. And here is an absolutely crucial architectural warning for you developers out there. Using IP addresses in the SAN field is widely considered terrible practice. In our modern cloud environments, IP addresses are highly ephemeral. They change, they scale, they get reassigned constantly. Tying a digital identity to a transient IP address creates incredibly brittle systems and significant security risks. The takeaway? Always bind your certificates to a stable DNS name.
So we have this digital passport, but we cannot simply accept it blindly. As the core principle of PKI states, think of a passport. The certificate itself is the passport, and the CA is the country that issued it. If you don't trust the country, you won't trust the passport either. Just because an attacker hands your application a mathematically perfect, tamper-proof certificate, well, that doesn't mean the connection is safe. If that certificate was issued by an untrustworthy certificate authority, or worse, a CA the attacker just quickly generated themselves on their laptop, it is the digital equivalent of being handed a driver's license drawn in crayon. Trusting the certificate inherently and unavoidably requires trusting the specific authority that issued it.
And just like physical passports, trust is literally never permanent. The validity fields, specifically not before and not after, establish a strict, non-negotiable window of time. Your application must check the current system time against these fields. If the current time is even a single second after the not after date, the certificate is completely dead and must be rejected. We enforce expiration aggressively to limit the blast radius if a private key is ever cracked or stolen. In fact, over the past decade, the industry has really pushed to shrink these validity periods dramatically, going from 5 years all the way down to just 90 days in the case of automated authorities like Let's Encrypt. This forces continuous key rotation and fundamentally shrinks the window of opportunity for attackers.
Section 3. Common Certificate Formats.
All right, this brings us to a huge source of friction for developers, the confusing alphabet soup of file extensions you inevitably encounter when trying to configure a web server. The key takeaway here is to never confuse the file encoding with the certificate itself. No matter what file extension you're actually looking at, the X.509 data structure inside is exactly the same. PEM, which stands for Privacy Enhanced Mail, is by far the most common format. It is simply the certificate data encoded in base 64 text. You can actually open a PEM file in any standard text editor and literally read the begin certificate header. DER, on the other hand, is the raw, unencoded binary format. If you see a file ending in .der, it's just raw bytes, which are more compact but definitely less human readable. And finally, we have PKCS#12, which you'll often see as .p12 or .pfx. This is a highly useful binary bundle format because a single file can securely store an entire chain of certificates right alongside the highly sensitive private key, usually protected by a password.
Section 4. The Chain of Trust.
So as we touched on earlier, not all certificate authorities hold the same weight. At the very top of the global hierarchy, we have the root CA. A root CA certificate is entirely self-signed, it's universally trusted by the tech industry, and crucially, it comes pre-installed by default in your operating system's trust store. It is the ultimate anchor of trust. Because a compromised root CA would allow an attacker to spoof quite literally any website on Earth, these roots are kept under extreme physical security. We're talking specialized hardware modules completely air-gapped from the internet and locked inside physical bank vaults. Because they're offline, root CAs do not issue certificates directly to end users. Instead, during a highly orchestrated ceremony, the root issues a certificate to an intermediate CA. The intermediate CA acts as a safer bridge. It actually connects to the network to do the daily operational work of issuing end-user certificates, completely protecting that ultra-sensitive root CA from daily network exposure.
Let's move to the next concept and see how this builds. The chain of trust is that hierarchical relationship linking a standard end-user certificate through those intermediate CAs all the way up to that ultimate root CA. When your application receives a certificate from a server, it does not just blindly verify that single file. It meticulously follows the cryptographic signature trail. It sees that the server certificate was signed by an intermediate CA, so it asks for the intermediate certificate. Then it checks who signed the intermediate CA. It follows this path upward, link by link, until it eventually hits a root CA that is pre-installed in its own local trust store. If that complete unbroken chain can be mathematically verified, boom, the connection is trusted. But if the chain breaks or leads to a route that isn't recognized by your operating system, your browser is going to instantly throw a massive security warning and terminate the connection.
Section 5. Verification and Revocation.
So the crucial point is understanding the actual algorithmic failsafes our systems execute under the hood. Verification really boils down to 3 critical steps. First, validity. The system checks the system clock to ensure we are currently sitting between the not before and not after constraints. Second, the digital signature.
The system uses the issuer's public key to mathematically prove that the certificate has not been altered in transit. And third, exactly as we just discussed, the system follows that chain of trust all the way up to a localized pre-trusted root CA. Every single one of these steps must pass flawlessly for trust to be established.
Step 2, verifying the digital signature, is where the heavy cryptographic lifting actually happens. To do this, your system needs a precise instruction manual, and that is provided by the signature algorithm field. This field tells the verifying system exactly which mathematical algorithms the CA used to sign the certificate. So, for example, it might be RSA or modern elliptic curve algorithms like ECDSA paired with a hashing function like SHA-384. Here is how that math actually works in practice. When the CA issues the certificate, it takes all the certificate data, runs it through the hashing function to create a unique digital fingerprint, and then encrypts that fingerprint using the CA's highly guarded private key. That encrypted fingerprint is the signature attached to the file. Then, when your client wants to verify it, it uses the CA's publicly available key to decrypt that signature back into the original fingerprint. Finally, the client hashes the certificate data itself. If the client's hash perfectly matches the decrypted hash, it is mathematical, undeniable proof that the certificate is authentic and has not been tampered with by some man in the middle.
But what happens when the underlying cryptography works perfectly, but human security fails? Listen, key theft leaves absolutely no technical trace on the certificate itself. If a sophisticated attacker breaches your server and silently copies your private key today, well, the matching X.509 certificate still looks mathematically perfect to every client in the world. The only real defense here is revocation. Historically, this meant adding the serial number to a static certificate revocation list, or CRL, that clients periodically downloaded. More modern systems use OSCP, the Online Certificate Status Protocol, to query the CA in real time, though honestly, that introduces its own latency and privacy trade-offs. But the core vulnerability remains human latency. Ask yourself, how long does it actually take for an organization to realize a private key was quietly exfiltrated, and how long until all the global clients communicating with that system finally download an updated CRL that flags the compromise? The gap between theft and revocation is a dangerous window where perfect cryptography actually works against you, blindly protecting the attacker. Digital trust is an incredibly powerful architectural tool for sure, but it requires relentless vigilance. Keep building securely, and I'll see you next time.